In this video, we're going to review how to use the Norton linkage software to generate position and velocity curves for a slider crank. Um, so one thing we need to do first, though, is when you do this, is set the preferences and switch to millimeters from inches, because our dimensions for this lab are given in millimeters. And then I'm just going to open the file that I already have set up here. Okay, so you can see that the crank is at 30, the coupler is at 90 millimeters. The offset is at 0 because the the axis of the slide is going to pass right through the origin, and then it's at a 45-degree angle. The distance out to the coupler point is 45 millimeters, and it's at 50 degrees. So this should look similar to what you would have on your on the box that you're going to use. So you can see here's the coupler point, and you're going to have to generate the curves, the plots. So just go to next and then plot. And I should say that sometimes you have to be careful with this software. Sometimes if some of the things you select, you don't get the right answers unless you start with the uppermost for the flyout, start at the top one. And so anyways, so if you do that, it seems to calculate correctly. So whether you're trying to do get the tables or the plots, just click on this top one first. Now we want to find the velocity and position of the coupler point. So we can go here, velocity of coupler point, x, y. So it'll be the x and y velocity coordinates, the magnitude, and the angle of the velocity. So this is one of the plots you want. So again, here's the x and y. This one is the magnitude, and this is the angle of the velocity vector right here. And then you're also asked to find the plot of for the angular velocity of the coupler. So for that one, of course, that's theta 3. I'm sorry, omega 3, right? Omega 2 is the angular velocity of the crank, and omega 3 is the angular velocity of the coupler. Okay, so in this particular example, we had set the angular velocity of the crank to 10 radians per second. So that stays up there, and of course, then alpha of the crank is going to be 0 because it's at a constant velocity. That shows you that. And then the angular speed, the angular rotation of the coupler is shown here. You can see it's oscillating back between negative and positive values, which makes sense. And this up here says alpha 4. That actually is alpha 3, right? Alpha 3. So this is the angular acceleration of the coupler. So anyways, that shows you how this is how you can get these plots that you'll need for this lab. Okay, and then each member of your team will, I'll just recalculate this. So each member of your team for this crank here, you can see as the crank goes to different positions, should select a position of the crank. And I will tell you that there are some positions that are easier than others. And you could also set this up to sketch up in SolidWorks. And then just as was demonstrated in class, you can use SolidWorks to find the coordinates or the distances for to the center of rotation, the instantaneous center of rotation. And then you can just use MathCAD to make the calculation. So I mean that's what I would suggest that you do is it's easy to sketch this out in SolidWorks, and then you can extend these lines so that you can find the instantaneous center and use driven dimensions, and that way you can get all the information that you need to use the method of instantaneous center. You should be able to do that fairly quickly. So anyways, this gives you just an idea of how to set this up, get the plot, and then you want to do the calculations using the method of instantaneous centers and compare your results to the plots that you got at the particular angle of the crank. In this video, we're going to look at some of the information about the motors that you'll need to complete the lab. And you're going to have to use the encoders on the motors and write your own software, write your own code to using the interrupts, so that you should not use already written encoder library. In other words, you want to write your own software to collect information on both the speed of the motor and how much it's rotated in the time. So I'm just going to go to this link here. So here's some information on the motor. It's a 50 to 1, of course, and you also have, there's some other information here, like the no load current. I don't think was given in the other one. And under resources, there is it looks like there's a MATLAB script here, so you can get the curves. But again, because the relationship between the speed and the torque and the current drawn in the torque are both linear relationships. So if you have these points, then you can easily write the equations, and if you want to plot, you can just create an Excel file to do that. But anyways, if we look back at this motor again, okay, so you can see that the wires, what each of the wires does is listed here, right? So these are the wires for the encoders, and then there's a quadrature. So in other words, it says that they're approximately 90 degrees out of phase. So if you're measuring an interrupt, suppose you measure this, there's actually 16 of these per revolution, but if you measure the rise and fall, so this is the low, this is high for one set, and this is low, and this is high for the other set. So in other words, if you measure each rise and each fall, then you actually get 64 counts per revolution. And with a 50 to 1, you can see that you end up with 3,200 ticks. Let's see, where is that? Yeah, so 64 counts here, and okay, so that information is back up the top here. So yeah, 64 times 50 is 3,200. I was thinking though that it's back down here. It says that it's approximately 90 degrees out of phase. I mean, if you have 16, say for the one side here of the yellow, if you have 16 rises per revolution, and it's a 50 to 1 ratio, so that's 800, basically 800 ticks per revolution. That's accurate enough. So what you could do to measure the speed, in this lab, you're going to output data at a rate of 50 hertz. So in other words, 1/50th of a second, every 1/50th of a second, you're going to output the angular position and the velocity. Well, you can get the velocity just by looking at the time it takes. In other words, record the time at each tick, and if you're just looking at the rise, right, then you know you've gone 1/16th of a revolution of the motor, or for the shaft, it would be 1/800th of the revolution of the shaft. And if you know the time when that happens, then you can figure out the speed very easily. So that's an easy way that you can determine the velocity at any given particular time. Is just look at the time it takes to go from one rise to the next. So anyways, in this lab, you have to collect data and output the RPM of the motor, or a plot of the RPM of the motor and the angular position of the motor. And for the angular position, as you get to 360 degrees, or if it goes, your angular value, position value gets above 360, then subtract 360 from it after the first revolution. So basically you reset to 0, and then after the second revolution, subtract 720 from it, and so on, so that you're always outputting values of angular position that are between 0 and 360 degrees. Okay, so then the other thing you're going to do in this lab is try and work out the wireless field communication. And what we've set up here is the task. If you can complete these tasks, then a lot of your programming that you'll need to do for your final project should be ready. In other words, because these will be very similar to the things that you'll have your robot have to be programmed to do for the final project. So anyways, hope you have a good time doing this lab.